All right, welcome to week 7. So now we're looking at quality control of Lidar. This lecture today is actually going to be relatively short, and normally is during the school year as well if we were actually in class. The reason being is I want you to explore this a little bit more on your own as well, because there's nothing more boring in life than somebody going through standards. There are some people who get really excited about it, and that's great. I am not going to sit here and tell you and dictate to you all of the different standards that are out there, because every jurisdiction is a little bit different. Alberta doesn't even have its own set of quality control standards, so I'm not even going to be able to provide you with that. But I do have some links that I've given you and provided you to explore a little bit further. And there's like the what's it called? Word scramble that I've given you. So use those activities to try to learn this material rather than me just telling it to you, because it's not very super exciting if I tell you everything. So this will be a shorter lecture than the previous ones. So what I'm going to cover today is I'm going to cover the quality control of terrain modeling, kind of what's included, and then factors that are affecting standards and guidelines, and then showing you what existing standards and guidelines kind of look like. The thing is, every year I seem to have people who get really confused between what factors are versus like actual standards. So I'm going to emphasize that a lot in today's lecture, just so that you don't get confused thinking, oh, well, these factors are actual standards. So we're going to spend a little bit of time discussing that and separating those two, because it's kind of one of those spots that I end up having to take off a lot of marks because people get confused between factors and standards. So I'm going to start with talking about the quality control of the terrain modeling. So make sure you do the readings in the textbook if you can. This reading, I guess I should point out, I'm putting this up here, this textbook should be available in the library, and this is not a required textbook, so just be careful that you're not looking in the required textbook. If you can get access to this one through the library, these are the pages to look at for quality control, because it's got all of that information in there. And this is kind of like the major, I guess, book of standards, and it is what we use for manual from the American Society of Photogrammetry and Remote Sensing. And they set this out and basically to try to standardize what LiDAR is supposed to look like and how everybody can share data and give each other, give your clients know what to expect when they get LiDAR. So this provides that structure. So I suggest especially taking a look at chapter 9 in that textbook. It is available in the library, and I have summarized it here, but again, more detail is available there. So quality control of terrain modeling, what does this include? So there are obviously different parts of terrain models that we have already talked about. There's so many of them. So one of them is contours. So we still use contours a lot. You'll see contours everywhere. Even though we do get like these nice 3D visualizations in computers nowadays, we still have many people that still need paper maps. And even those 3D visualizations, we will still put contours on them because it does provide a really good visual reference and mathematical reference for ourselves. So what we're doing when we're generating contours on a DTM from LiDAR is we start with very highly dense points, and then we create contours from there, and then we keep lowering the number of points to smooth out the contours. So you can see here that we have very noisy contours, and then they're slowly reduced down to smoother contours that actually cover that actually make it look easy to read, right? So that's what we're really going for. If we are using break lines, they need to be entered before we reduce the point density. So here, if we had a break line, for example, up here, looks like they may have had a break line that they were using, so they implemented the break line up top here before reducing the point cloud, so they could still maintain those lines that we're seeing that are up here. We also If like, for example, if we were to have like perfect conditions, so we're looking at a perfect condition situation, we have these beautiful break lines that are exactly perfect. There's no variation to them whatsoever. We know that they are fully accurate and better accuracy than what we have for the Lidar. And then we have the absolute minimum number of mass points outside the break lines. So we've managed to decimate our point cloud to a point that the mathematics that we're using in our terrain are able to process faster because we've managed to reduce those points that are just really redundant rather than helpful. So that's the ideal situation. It doesn't necessarily always happen, but you can see here how noisy, how you take your noisy contours and then you reduce them down, and this still maintains that accuracy. It just helps generalize it a little bit more. So the quality control of the terrain modeling itself, so if we're creating a 3D model and bringing that in, it really depends on the vertical accuracy that we are required to have. So that's going to dictate what kind of model you're going to use. So if you're using tins, or you're using rasters and you're creating a rasterized 3D model, you're definitely going to see differences in how it's displayed, and you're going to see differences in accuracy. So if we have, for example, a tin, and I wanted to measure like from the bottom of this cliff to the top of the cliff, then, is my tin accurate enough, or am I able to choose the points accurately enough to be able to get that? If I'm trying to find gaps between these, is my model, does the vertical accuracy affect my horizontal accuracy? Because they trade off a little bit, especially in LiDAR. And am I able to get that distance between the two? Okay, so that's what these arrows are pointing for me. Anyway, if you go over to the number 2, they actually have a different meaning, but I'm going to use them for my own purposes. So they also, you might not need break lines, for example, in a 3D model, because you have enough information to be able to create that visualization. And if you're able to like just draw, choose a point to another point, this solid surface is much easier to use than a point cloud that looks like this, especially if I'm trying to identify like between these two, like down here. I have these two here. Can I actually see it here? Well, maybe, but if I'm trying to get that distance across, am I really going to be accurately choosing it or not? And this cliff here, I can see these lines, but where's the top of it? At what point do I find that top? So making a solid surface is going to make it easier for your client rather than leaving it as a spaced point cloud like this. The only time that you really need break lines, though, is if you're doing hydrographic applications, so you're looking specifically at drainage. And so I really highly suggest with when you're doing drainage, you're going to have like very high dense, you're going to have dense point clouds, not as dense as some applications, but you're going to have dense point clouds, and you really need to have a lot of break lines in hydrography. So because that sloping is really important to capture. So with terrain models, it says that 1 to 2 meter spacing is adequate. That's for like general terrain models. Hydrographic is going to be a little bit more, is going to be denser. But you can imagine, like, if I was trying to do like every centimeter or every 20 centimeters in this whole point cloud would be a solid. Anyways, here I'm actually creating the solid surface, and the modeling component allows me to have that statistical analysis on top of the points. So that's why models are really important to use rather than strict just points themselves and just dense points. Another terrain model that we use is urban modeling. So this is looking at the city. Now we are really truly concerned about like details of the city. So you can see in this point cloud example, we can see like where possibly balconies are and windows are. This is all about you can use this for combat planning, you can use this for urban design, you can use it for like architectural planning, landscape planning. There's a lot of stuff you can do with this for sure. But you can imagine if you are a city police and somebody's being held hostage in one of these buildings, how are you going to get in there? So there is, and how, what are your escape routes if something goes wrong? So there's a lot of stuff that you can use for those planning. And of course, that's an extreme case. That's like Hollywood style stuff. But it does happen that, there is a need for that kind of planning. So we do, for 3D urban planning, we need high quality. So we need to be able to see the different parts of roofs. We need to be able to see that the visual quality needs to be very high, and we need to have very high definition. So you can see how, again, what is a tree? Where are my pathways? It's showing cars there, but this is a really good example. What are the sides of the building? So I'm going to need to do several passes over this so I can see the size of the building. We're more interested in really the detail rather than the accuracy, right? So we're talking about high quality, high definition. So if you were to put something on your computer screen, let's say like an HD computer screen, and you were playing a video game, do you really care about the accuracy of the terrain around that video game? Probably not, because you're not going to sit there and measure the centimeters. Because I've seen video games where, I think it's like Fortnite, maybe even, that you can actually press into the wall. Your guy goes into the wall and you can be shot on the other side of the wall. So that high detail capture is so much more important. The centimeter accuracy level, sure, yeah, that's a programming glitch. You can pass through the wall, but you don't really care how long that wall is to a centimeter. What you really care about is where does it visually end so you can get around it, right? So that's the difference. You don't care whether it is what is the exact latitude and longitude or UTM coordinate of the top of this building, and where is this precisely located with respect to an earth fixed system. You don't care about that. What you care about is where is it relatively and how can I get there, right? So you want to know those details. So this, 5 to 10 points per square meter is usually sufficient compared to the terrain models, which is 1 to 2 meter spacing. So these are obviously 20 centimeters is good, right? 10 centimeters is probably even better, between each point. But that's what this is looking for. So you will need to do several passes in order to do it. The last one for quality control is looking at biomass and forest modeling. So if you were looking at a forest, what are the things you need? Basically, full waveform digitization is needed for really good biomass modeling, because you were trying to figure out how much vegetation is there. You were trying to figure out the types of vegetation that's there. What are the heights of the trees? Because that's also used as a measure for age. How thick are the trunks? All of that really comes down to needing full waveform digitization. You can't do that with a time of flight digital response, which is just one bump saying, hey, I've detected a signal. Hey, I've detected a signal, right? So we've seen this kind of graph quite a few times, showing this leading edge peak and everything. I've already downloaded this and put this in a previous slide. So if we're doing that and we're trying to come up with this, which is a different reference, this is telling me how much biomass I have in different areas. And so it is classifying it based on return, and it was showing the scan direction. And they've used hexagons instead of pixels, so that's also something really unique with forest modeling. They do all kinds of neat stuff. So anyway, so you can see how much vegetation is at each level and where is it located. So it's a really good quick visualization, but you need to have this full waveform digitization to do so. So if you get into forestry and going to get into forest modeling, this is actually a really fascinating aspect of Lidar, and becoming a Lidar expert in forestry is really pretty cool. So now we're going to talk about factors that affect accuracy and that affect the standards that are done. So the difference between a factor and a standard. A factor says these are the things that impact or that are having to be taken into consideration in order to create a standard. So this is the starting part before we actually create a standard. So think of this as step 1 before the standard. So I broke this up into the titles in the textbook, but but really they come into really good categories as to how the standards have been developed. So our planning stage, this is at the very beginning before you go out and do anything, you need to know the acquisition parameters of the sensor. Now, obviously, you guys don't get to do that in this project because I'm like, here's your Lidar data. But if you're actually to go out and do it, you need to know your acquisition parameters. And all of those parameters include things such as the light, what type of light, the pulse repetition frequency range, really the flying height threshold, like what is too far away at what point. And even your like IMU and your GPS, what are those parameters? You have to know all of those. You also have to know the environment, what's happening. LiDAR doesn't work in fog. So if you are living in Vancouver and you want to come in and you want to like do a LiDAR scan of an area in Vancouver, you need to know when it's not going to be foggy and when there's not going to be dew on the ground, when it's not going to be raining. So you need to have that nice sunny day. So that's really an important aspect. Then also like everything about the flight. So knowing how long your flight lines are, your altitude, your ground control configuration, the number of ground control points you have, GPS quality and the IMU quality. You need to know all of that before you get out there. Obviously the GPS and IMU are kind of separate packages to the laser scanner. So you do have to make sure you manage that. As well as the differential GPS, you have to know those baselines, right? So that's another important part. And also know what software you're going to use. So if you're going to use ArcGIS, are you going to switch everything into rasters for analysis? Are you going to be using CAD to create lines? All of that impacts, these are all factors that impact the standards that are coming up. Then we have our next section, which is sensor orientation. So with our sensors, we need to know how they are oriented. This is the calibration, right? We're pretty much calibrating everything. So we have an exterior orientation parameters, which is all related to taking our points and putting it into the real world. So you can think about it as the LiDAR observation equation, because we are trying to take all of these pieces of information and we're trying to orient everything externally so that they all match into one single coordinate system. The bore sighting process, how did we get the sensor on board? How was it secured? Did you have to calibrate it on the ground? When was the last time it was taken in for like just maintenance? All of that stuff comes into that bore sight process. Also looking at the standard deviation between the flight lines, right? So the flight lines might be a little bit longer or shorter depending on the area that you are in. That will make a difference. And then looking at your residuals of your ground control as well. So after you have collected all your GPS data, what does your ground control error look like? Then the IMU also is a factor. So you need to bore sight your IMU, so that is determining those lever arms. Then we need to correct the flying altitude. So, are we actually at the right flying height for the sensor versus like what point density we want, plus like does it match with the pulse repetition frequency that we are working with, and then also the speed of the aircraft. If you go too fast, you are now reducing down your point density because the points are further spread apart. The distance from the GPS station is also part of this orientation. So again, that baseline, how far is it? The calibration procedure that we go through also impacts the standards. So how well has it been calibrated? And then the mirror motion, because obviously a Palmer scanner is very different from an oscillating mirror. So how that picks that up, that each of these parts are going to impact how the standard is set up for that particular sensor. The next one is height bias. So with height, we have an ASPRS standard that says that footprints are supposed to be within 1 foot of its actual location. So that's pretty tight, right? Like you think 1 foot is 30 centimeters, and yet our horizontal error budget is really about 30 centimeters. So what can we do to improve that if we were looking at building footprints? So this is part of this is really part of like our standard, not the standard itself, but the factors affecting the standard. So the building footprint, it has to be horizontally within 1 foot, but the height, so then that height bias, if it's out more than that, it's going to actually affect your entire data set, right? So what I want you guys to think about is like how do we verify that? So we have our Lidar data, we might have rooftops over top of it, but where's the building footprint? Where is it located? And how do we verify that after the fact? Because we can't really be out there collecting the exact location with respect to the aircraft, right, on the ground. So how do you verify that? So these are all challenges that we are thinking about when we're creating Lidar data sets. So we can combine photogrammetry and Lidar together, which is done quite often. We also use photogrammetry to create break lines, which is also very helpful. But we still struggle with the fact that photogrammetry has a different accuracy and it has a different kind of distribution, right? So Lidar is points, photogrammetry is raster, and then the orientation of the pixels for the photogrammetry may not fit the same orientation of the pixels that we create for the Lidar. So we end up with all kinds of crazy problems that happen, and these are all things that need to be overcome. Generally speaking, they might have a slightly different scale. If Lidar really doesn't have scale, except when it's on the screen, like the actual computer screen, but it's not collected as per a scale because it's collected as a single point, where photogrammetry does have a scale that's applied as soon as it's collected. So we have all kinds of crazy things that happen. Of course, with photogrammetry, the height is not scaled. It's considered an unscaled value. And again, Lidar is not scaled until it's put onto a computer screen. So we have to build that. How do you like really match all of that? It's a lot of things to think about. There's a lot of factors that go into. You never thought that Lidar was so crazy and like had so many different parts to it, right? So I want you to think about this. I want you to think on both sides of the argument. Will the error budget of Lidar systems allow you to detect 1 foot contours? Why or why not? And why both? If there is both. Then do we need break lines when we use Lidar? Why or why not? And then how are they used? Right? If we don't use break lines, then obviously we don't need them, and why not? But if we do use break lines, how do we use break lines in Lidar? And I've already talked a lot about that in previous sections, but there is some stuff out there that talks about break lines with Lidar. Some argue for break lines, some argue against. So make your decision on that. I may make this part as a question in the discussion, just to see what people put like as a 1 point thing. So other things that can affect the standards, and these are all factors. So is the mirror shaft encoder sensitivity and stability. So this impacts errors, right? So how do we handle errors? So that alone is really like the mirror itself within the actual sensor. We don't have a lot of control over, but it does have, its sensitivity and stability is a big deal. So this actually helps govern the standards for developing a Lidar system. Atmospheric refraction models, that's all post-processing stuff. So we're still dealing with GPS, we're still dealing with light passing through the atmosphere. So how do those two come together, right? So we have to have different models. So there are errors that come with that, and then there's standards that help manage those errors. We also have sensor attitudes. So how are they in space? What does that look like? And then finally, the last error that we can come across is thermal stresses. So when you fly high in the air, it's a lot colder up there than what it is down below. So if it's colder out there and it's warmer in the actual airplane, then we have a thermal stress that's being put onto the equipment. So, and again, we know that thermal stresses can cause light to change as well, right? Because of density, temperature affects density. So again, another error. So how do we manage that? And that's why the standards have to include these components as well. The nice thing is with these errors, these 4 particular errors, we can model them to minimize them or remove them. But again, there are standards that have been created to be able to manage that, to help you follow through. So the overall effect, what happens? So precision of Lidar using all of the standards can vary from millimeters to a few centimeters. So that's our precision. The GPS error in Lidar is 1-to-1. So if you have a 4 centimeter error in GPS, you are going to have a 4 centimeter error in Lidar. It just transfers over really nicely that way. We do have horizontal errors and vertical errors based on flying height, based on the distance to the ground, which can, really from the nadir, or sorry, distance on the ground from the nadir. So this is like how far away from the center line that we're looking at, right? So it's kind of like the relief displacement. And then we have our angles at which the attitude of the plane is. So we have roll and pitch. You guys are familiar with that. The heading is yaw. So that's another error in the horizontal error. So you can calculate these. I'm not going to ask you to do that, but just to see how these are related. So GPS is 1-to-1 throughout Lidar. Then we have direct relationships with the distance from the ground, on the ground from the nadir. So how far away from the center, the yaw angle, the flying height, the roll angle, those two go into the horizontal error. They feed into that. And then the vertical error is directly related to the distance on the ground from the nadir and the roll or the pitch. So you can calculate them equally. You can use either or. Usually we'll use the greater of the two if they're coming up differently. But so the vertical error essentially should be 0 at the nadir, which should make sense. Again, this is based on sensors. It's not necessarily based on everything else. But truly at the nadir, there should not be any error that's being included unless it's a GPS error added on to all of this stuff, right? So this is the overall effect. This is after you've implemented all the standards. This is how you would calculate everything. So getting into actual standards. So here's our error. You don't need to calculate this. This is just giving you an idea of the relationships that you're going to see with error with respect to those factors. Because we've talked so much about errors in this. So how do we actually manage this? Because at this point, you guys are all probably sitting there going, well, LiDAR is not accurate at all, but yet we use it all the time. And if you were to take photogrammetry, you have even more errors that get added in, but where they're all being modeled, right? So every time we model errors, we can improve the accuracy because we can reduce or minimize those modeled errors, just like in photogrammetry. So we have some existing standards and guidelines. Like I said, I'm not going to go through all of these. I'm just going to point out some stuff that is important through these. You guys can read the PowerPoints later, but you also have the activities that I'd like you guys to do. So here's data collection. So here's some of the stuff I'm dealing with, the actual raw point cloud, not the actual product. So this is at that very beginning stage. There are a couple slides on the data collection standards. So again, that's like, what are we looking for? What are the numbers that we're aiming for? So for example, overlap must be greater than 10%. You need a buffer of 100 meters around the collection area, et cetera, et cetera. So then we have the data processing. So this is going through to create the final product. So your data eventually must be in a last file format. You're here for American standards, it's UTM. You will see some of the coordinate systems in 3TM, but it should be in a TM system when you go to give it to a client. Metric units, because it's in a TM system, right? So just a few of them there. Some more for creating the final product, looking at all points must be classified. So we say that there's unclassified, but here, if they're unclassified, they're considered noise, but they can be put into an unclassified class because they become class. Classification accuracy must be less than 2%. So I would like you to think about what we did with remote sensing, and if you were able to do a classification, a supervised classification with less than 2% error. So that is what is expected in Lidar. We're not doing the classification in our class, but because they're already pre-classified, but this is adding to that final product. Then if you're dealing with water, water also has its own special sections. So here's just a few examples of that. Again, I'm not going to go through them. You can definitely go through and check them out. But just little things like streams are represented as lines whenever you provide a product from Lidar. How is non-tidal water versus tidal water represented, etc. And then our actual deliverable standards. So here, they must include all the information that's up here. They need to classified, need to be there. The DEMs must have these kinds of compatibilities and standards. So again, you can read through them. They're all for you to check out. And here's what Alberta does, right? So we have 3 different standards that we try to follow. Depends on the project that we're doing here in Alberta. Depends on who we want to talk to, who our client is, what their expectation is. So we have the ASPRS standards. So there's a whole PDF online that you can go to. There's also the Canadian standards that NRCan has put out. So you can go there and check that out. I do suggest using this one because that's one of the word searches. Then we have BC standards. They also have put out their own LiDAR specifications because they use a ton of LiDAR, and in fact their LiDAR is like all free in their open data. And then here's an example of something that somebody did in Alberta, so you can just check that out. We don't actually have our own standards, but we generally follow Canadian or BC. If you have an international client, though, they will use the ASPRS. So that's why I provide you with all of those so that you can check it out and work from there. So here's some of the references of my little images that I checked out. But that is quality control. Like I said, this is a little bit shorter of a slideshow. Next week, we are talking terrestrial laser scanning, and that is the last one. So today we talked about what are some of the quality control processes that you can follow to keep your LiDAR data set accurate. Then we talked about the factors that have been implemented into creating accuracies. And then the last thing was just really quick run through of some of the accuracies, or it's not accuracies, standards that are out there. And so those standards are the actual values, so that is an actual standard. So yeah, so that is everything for quality control, and we'll see you next week for terrestrial laser scanning.